our first example of the time-independent Schrodinger equation. Section 2.2, the infinite square well. Suppose the following. We have a potential, depends on x, where it is from x equals 0 all the way to x equals a, and it is infinity otherwise. So it creates a potential that looks like this. Right here past 0 and over here past a is infinity, and right here between 0 and a is 0. So it just creates a box infinite square well. That's where the name comes from. Figure 2.1 up there. A particle in this potential is completely free except at the two ends, x equals 0 and x equals a, where an infinite force prevents it from escaping. A classical model would be a cart on a frictionless horizontal air track with perfectly elastic bumpers. It just keeps bouncing back and forth forever. This potential is artificial, of course, but I urge you to treat it with respect despite its simplicity, or rather precisely because of its simplicity. It serves as a wonderfully accessible test case for all the fancy machinery that comes later. We'll refer back to it frequently. So this is one of the most simple models that you can solve the Schrodinger equation in, but you should still respect it because it gives you a lot of interesting properties of quantum mechanics that may be useful, or that will come up later. Outside the well, psi of x, little psi, which I'm just going to call psi from now on. This is only the position dependent. We did this in separation of variables. The probability of finding the particle there is 0. Inside the well, where v equals 0, the time-independent Schrodinger equation reads, so this is the time-independent Schrodinger equation. Since v equals 0, we used to have an extra term over here right after this, which is plus v times psi, but now v is 0, so we just equate that to 0, and this equation simplifies. Now we can move some parameters around, so multiply or divide both sides by this minus h bar squared over 2m. We bring it on this guide, and then we create this new variable, this substitution. We call this k, and we have k squared over here. So the Schrodinger equation for v equals 0 becomes this. By writing it this way, I have tacitly assumed that e is greater than or equal to 0. We know from problem 2.2 that e less than 0 won't work because equation 2.24 is the classical simple harmonic oscillator equation. The general solution is sines and cosines, a summation of them. So this equation yields solutions of sines and cosines. The way I think about this is, what equation equals its second derivative and a minus squared constant? So if you differentiate cosine or sine 2 times, you'll get back to the original one, and you'll spit out a constant here, which comes out from the inside argument of the sine or cosine. So a and b are arbitrary constants. Typically, these constants are fixed by the boundary conditions of the problem. What are the appropriate boundary conditions for psi of x? Ordinarily, both psi and the derivative of psi with respect to x are continuous. So this is pretty important. I'm actually going to highlight this. Let's actually read number 11 as well. That's right, psi of x is a continuous function of x, even though psi, the big function, need not be. That's interesting. Why is the full wave function not forced to be continuous? Who knows? But where the potential goes to infinity, only the first of these applies. So only psi has to be continuous, not the derivative. So the derivative could be discontinuous at the boundaries. What discontinuous means is just there's like a little kink in the function. It's not like a nice smooth differentiable function. There's a little bit of a kink where the derivative approaching one side and the derivative approaching the other side are completely different. So there's no derivative. There's no exact derivative exactly at that tip there. That's what a discontinuous derivative of a function means. I'll justify these boundary conditions and account for the exception when v equals infinity in section 2.5. For now, I hope you will trust me. We will, Mr. Griffith. Continuity of psi of x requires that psi of 0 equals psi of a equals 0. So the wave function at the boundaries equals 0. So as to join onto the solution outside the wall. What does this tell us about a and b? Well, we plug in psi of 0 equals a sine, and then we we make this x equals 0, plus b cosine, we make this x equals 0, equals b. Why does this equal b? Because sine of 0 equals 0 and cosine of 0 equals 1. So this just gives us b. So b equals 0 because of this equation and because of this equation combined together. Hence, we simplify the wave function psi of x equals a sine kx, and then we use the other boundary condition. So we use this one. Before we use this one to eliminate b, now we use this one to see what else we can figure out about a perhaps. So psi of a equals a sine ka. So either a equals 0, in which case we're left with the trivial non-normalizable solution psi equals 0, which we don't like, or else sine ka equals 0, which means that ka is equal to 1 plus or minus pi plus or minus 2 pi plus or minus 3 pi, because sine of any integer multiple of pi, positive or negative, or 0 gives you 0. So that makes this equation here valid. So we get this constraint from applying one of the boundary conditions. But k equals 0 is no good. Again, that would imply psi of x equals 0. We don't like psi equals 0 because then we don't really get an interesting solution from the Schrödinger equation. We just get that the probability distribution of the particle is 0 everywhere, so there's no particle anywhere, which is stupid. Or not stupid, but it's like trivial, it's kind of boring. And the negative solutions give nothing new, since sine of negative theta is equal to negative sine of theta. So we remove the negative solutions, and we can absorb the minus sign into a. So the distinct solutions become k subscript n equals n pi over a, with n equal 1, 2, 3, and so on. So this quantization condition comes from the boundary conditions of the particle in a box potential. Very cool. Curiously, the boundary condition at x equals a does not determine the constant a, but rather the constant k, and hence the possible values of e. So here we got the e values, they got a subscript n, they equal h bar squared k subscript n squared divided by 2m, or if we replace kn with this stuff, we have n squared pi squared h bar squared divided by 2m a squared. A being the size of the well, the infinite square well, h bar is a constant, pi is a constant, 2m are constants, m is the mass of the particle from the Schrödinger equation, and n squared is this quantized parameter, which is just the positive integers from 1 all the way to infinity or whatever. Maybe not infinity, but all the way on for an indeterminate amount of time. In radical contrast to the classical case, a quantum particle in an infinite square well cannot have just any old energy. It has to be one of these special allowed values. 12. Let's read 12. Notice that the quantization of energy emerges as a rather technical consequence of the boundary conditions on solutions to the time-independent Schrödinger equation. This is crazy. Highlight this. To find A, we normalize psi. 13. Actually, it's psi, the full psi of x comma t. That must be normalized. But in view of equation 2.7, this entails the normalization of psi of x, just the small psi, position dependent. So we can normalize the regular stationary state psi, and we should get the full psi normalized. Anyway, we normalize over all space. In this case, it's from 0 to a, because anywhere outside of that, the wave function is 0. We have the solutions, which are these guys, and it's absolute value squared. On the sign, we don't need the absolute value because it is not a complex number or anything like this. The a can be pulled out, integrate over sine squared. We don't know how this happens, but integrate, plug in the boundary conditions here, and we get absolute value of a squared is 2 over lowercase a, this being the width of the box. Now we can plug that a back into the equation, and we get the full solutions. This only determines the magnitude of a, but it is simplest to pick the positive real root. A is equal to square root 2 over a. The phase of a carries no physical significance anyway. Inside the well, then, the solutions are sine waves. And here we have psi 1, psi 2, psi 3. As you change n, the wave function changes. And so does the energy, because we have an energy dependence on n over here. As promised, the time-independent Schrödinger equation has delivered an infinite set of solutions, one for each positive integer of n. The first few of these are plotted in figure 2.2 right here, They look just like the standing waves on a string of length A. Psi1, which carries the lowest energy, is called the ground state. The others, whose energies increase in proportion to n squared, are called excited states. So this is the first excited state, the second excited state, and so on. As a collection, the functions psi n of x have some interesting and important properties. Here they are, 1, 2, 3. We have a proof. They are alternatively even and odd with respect to the center of the well. Psi1 is even. You can see with respect to the center of the well, it is even because the left side of psi is the same as the right side of psi. Psi2 is odd, so we cut the well in half. This side is completely opposite from this side. Psi3 is again even, and so on. That's important to know. As you go up in energy, each successive state has one more node, zero crossing. Psi1 has none, the endpoints don't count. Psi2 has one, so it crosses the x-axis once. Psi2 has two, or Psi3 has two, and so on. They are mutually orthogonal in the sense that one value of n, let's call it m, multiplied, or complex conjugate of this multiplied by another one of n is equal to 0 if m does not equal n. So this is called orthogonality. It's like taking the inner product of these two guys. Basically, you take an integral, one of these complex conjugate it, the other one keep it as is, and then the m and n values, if they are not the same, you get 0 here, which means they are orthogonal. Here's the proof. We're not going to go through this proof. We might look at this a bit later in detail. Note that this argument does not work if m equals n. Can you spot the point at which it fails? In that case, normalization tells us that the integral is 1. In fact, we can combine orthogonality and normalization into a single statement, orthonormality. So this value here means if m equals n, this equals 1. So this is just the normalization condition. If m does not equal n, this equals 0. So it's the orthogonality condition. Here it is over here. This is called the Kronecker delta. We say that the psi's are orthonormal, so they're normalized and they're orthogonal to each other as you change the value of n. They are complete in the sense that any other function, f of x, can be expressed as a linear combination of them. F of x is equal to the sum of these cn's, these are like probability amplitudes, of these psi n's, which we located them. They are these sine functions. There's an infinite number of them. And this thing equals basically this once you plug in the sine and pull out the a squared normalization term. So you can create any function depending on what these cn's are. This is like the Fourier series using this basis set of wave functions to create a whole other new function that looks interesting and is a combination of these guys. This is also superposition here. I'm not about to prove the completeness of the functions, but if you've studied advanced calculus, you'll recognize that equation 2.35 is nothing but the Fourier series of f of x, and the fact that any function can be expanded in this way is sometimes called Dirichlet's theorem. Let's check 16. For example, it's just an example. No need to check that right now. We're just reading, getting some cool theory in our heads. The coefficient Cn can be evaluated for a given f of x by a method I call Fourier's trick, which beautifully exploits the orthonormality of the psi n's. Multiply both sides of the equation 2.35, right here, by psi m complex conjugate and integrate. So on the first side we have f of x, multiply that by psi m complex conjugate, integrate. So here we have like the inner product of this psi m complex conjugate with this f of x. Then we see in here, we got a psi m. Since the cn's are constant with respect to dx, we can pull that out, but we still have the summation sign over here. Then this over here gives us the Kronecker delta, which was introduced over here, right? And we saw that this thing here equals the Kronecker delta. So since we see this thing here, we can replace that with the Kronecker delta. And if we have a sum over here, it means that each time we sum over this, the Kronecker delta is only going to pick out the cn's that match the m over here. So anytime n does not equal m, it's going to be 0. But anytime n equals m, you're going to pull out 1. So that the only time that happens is when the cn equals cm. If that didn't make sense, don't stress about it. I'm just kind of ranting about it. Notice how the Kronecker delta kills every term in the sum except for the one which n equals m. That's basically what I said here. Thus, the nth coefficient in the expansion of f of x is Cn. This is a way of calculating these Cn's over here, which you can use to create any function using the basis set of the sine and cosine function, or sorry, the sine functions we found from the square well. So these are the stationary states of the square well. If we find a specific probability amplitude Cn for each of these basis sets, we can create any other function that is also a solution to the Schrodinger equation with the square well potential. That might sound kind of crazy, but here it is. Basically, you take an integral with the psi n, complex conjugate, and f of x. We're going to look at an example of this later on, so don't stress about it. These four properties are extremely powerful, and they are not peculiar to the infinite square well. The first is true whenever the potential itself is a symmetric function. The second is universal regardless of the shape of the potential. Orthogonality is also quite general. I'll show you a proof in chapter 3. Completeness holds for all the potentials you are likely to encounter, but the proofs tend to be nasty and laborious. I'm afraid most physicists simply assume completeness and hope for the best. The stationary states of the finite square well are boom. So we just slap on the wiggle factor and we get the full stationary states. I claimed equation 2.17 that the most general solution to the time-dependent Schrodinger equation is a linear combination of stationary states. So that's where we use the Cn's. And boom, here we got the full wave function with x and t. It is a summation from n equals 1 to infinity. So this is a Fourier series. We get the Cn terms, which we found up here, which is a whole ass integral. The normalization constant, the stationary states of the infinite square well, which we found earlier, and the wiggle factor. Over here is the energy. So yeah, looks a little crazy. Don't stress about this, guys. Let's keep reading. If you doubt that this is a solution, by all means check it. Damn. It means it remains only for me to demonstrate that I can fit any prescribed initial wave function psi x of 0 by appropriate choice of the coefficients Cn. So this is very important here. Psi x comma 0, this is some initial at time equals 0 wave function, and you can create it by psi subscript n, which is the stationary states of the square well which we found, multiplied by these coefficients. And these coefficients, again, you find using this way, except you just replace this f with your original wave function psi, which is shown over here. Cn, here we put the this equation here, which we found earlier, normalization constant, sine, and then we multiply it by our original wave function. The completeness of the psi's, confirmed in this case by the Dirichlet theorem, guarantees that I can always express psi of x at t equals 0 in this way, and their orthonormality licenses the use of Fourier's trick to determine the actual coefficients. That does it. Does in italics. Given the initial wave function psi of x at t equals 0, we first compute the expansion coefficients Cn using equation 240 here, and then we plug these into equation 239 right here to obtain the full wave function. Armed with the wave function, we are in a position to compute any dynamical quantities of interest using the procedures in chapter 1. So remember, in chapter 1 we saw that the wave function psi is a probability distribution. With probability distribution you can find averages, things like this. So go back to chapter 1, which I did a full read through on this channel if you're interested in this. At this same ritual, and the same ritual applies to any potential. The only things that change are the functional form of the size and the equation for the allowed energies. Here's an example. We're going to just skip the example very quick and read here because that is the end of the chapter with some of these problems. So let's just finish reading and then maybe we could take a look at one of the examples real quick. Of course, it's no accident that equation 220 came out right in the example 2.3. Indeed, this follows the normalization of psi. The Cn's are independent of time, so I'm going to do the proof for t equals 0. If this bothers you, you can easily generalize the argument for arbitrary t. 1 is equal to the normalization of the initial wave function, which equals this and this. Oh boy, what's going on here? Ah, this thing here. So where do we see this? Do we see this in the example? C ends. Maybe the example is important for this little ending section. Let's just keep reading. Again, the Kronecker delta picks out the term m equals n in the summation over m. Similarly, the expectation value of the energy, equation 2.21, can be checked explicitly. The time-independent Schrodinger equation, equation 2.12, says here, Hamiltonian times psi subscript n, the solution to the infinite square well, equals E subscript n, the energies of the square well, and again, the wave function of the square well. So, expectation value of the Hamiltonian is sandwich it between psi star psi, integrate over all space, replace psi star with this thing, the summation that we found. Where did we find this? See this earlier here? Here? No, that's not it. Not here either. Here, huh? Boom. Yes, I think that's chill. Okay, maybe a little too much theory from this section. Let's see what's going on here. And then replace the psi star with just this one with the n, right? We got one of them is m, one of them is n. And then we pull out the summation signs, boom, to the front. We pull out the CMs and CNs, but remember one of the CMs is complex conjugate, so that is shown here. And then we have an integral psi subscript m star times psi n over dx. Then this normalizes to 1, so we get this. Actually, it doesn't normalize to 1, my bad. It equals the Kronecker delta. It's only 1 if m equals n, and it's 0 if m does not equal n, so that's the Kronecker delta. Everything here stays the same. Oh, and this is interesting. Check out this sum. This sum goes over all of the n's and all of the m's. But since we have the Kronecker delta, every time an m and an n are different, everything here equals 0. The only time it does not equal 0 is when m equals n. So both of these are n. So one of these can be removed. You get just a sum over n or m. You can choose whichever letter you want because now we remove something. And since here you get psi star psi, this becomes absolute value squared of these guys. The Kronecker delta picks out the term n equals n in the summation over m. Similarly, the expectation value of the energy. Okay, I think I read this and was reading this instead. Same kind of procedure, except now we have expectation value of the Hamiltonian instead of just the psi star psi. And we get the same thing, summation of these coefficients squared. But here we have an en because we took the expectation value of the Hamiltonian. Here we only had 1 because we started off with 1, the normalization of this. Okay, let's check one of the examples, but this is the chapter. And the next thing is the harmonic oscillator. So kind of crazy, guys. I understand. It is quite crazy. Let's check the example, though. Every time you read some theory, the theory always is very mind-blowing. And then you do some examples. The first example is weird. The second gets a bit easier. The third, the fourth, the fifth, you'll get it. A particle in the infinite square well has the initial wave function, psi of x at t equals 0, ax times a minus x. And it is existing between 0 and a. So here's what the wave function looks like. They even show you the maximum point over here. For some constant a, see figure 2.3. Outside the well, of course, psi equals 0. Find psi of xt. So how do we do this? Well, we have to do this over here. We have to find this full psi. And how we do that is we are given this, right? And we can find these guys, plug these guys into here. That's how we'll get this. And here is where the information of our wave function goes. So in a step-by-step basis, you are given psi, the initial wave function at time equals 0. It is some random function. It's not a sine function or cosine function or something else. It is just a random function that looks like this, boom. You plug this function into this integral over here, and you have to understand that what you're trying to do here is figure out how you can create this function in terms of the basis functions of the solutions to the Schrodinger equation with the infinite square well potential, which is what we see here. We plug this in here, we plug this in here, we integrate, and we get Cn. How are we getting this? We are getting that from this equation here. So you could take a look at this proof. This Cn tells you how you can create a function f in terms of different functions psi n. So over here, f of x, you can create this function by doing Cn times psi n and summing that over all of the n's. In this case, our psi n is the basis vectors or basis functions of the infinite square well potential. So this is how we are starting the problem. We find the Cn's by plugging in our thing here and doing this interval, right? If you're given this, everything here, you can integrate and you can do it. It might be hard, but you could do it. Cn now gets plugged into here to get you the full wave function, right? And everything in here is known as well. We know all this, we know all this. All we're looking for is the Cn's, and this is an infinite sum. So this is how we're gonna do this. Let's see how they do it in the example. Solution. First, we need to determine a by normalization. Okay, in this problem we normalize because a is an unknown constant. All right, so one extra step. We normalize this. 1 equals integral over all of space, in this case all of space is from 0 to a, of the absolute value of the wave function squared. So absolute value of this thing. We pull out the a squared because it's a constant. Now we have an x squared, we have a minus x, all of that squared. We integrate this. He doesn't show the integration because it's a physics book. If you don't know how to do integrals, put this into an integration calculator or just check some integral book. You know, refresher integration. I honestly don't know how to do this. I might have to distribute stuff. Boom, and then apply these bounds over here. Then we get this. So a absolute value of a squared times lowercase a to the fifth over 30. All of this equals 1. And then if we solve for a, we get a is equal to root 30 over a to the fifth power. Nice. Now, the nth coefficient is, by equation 240, here equation 240, we compute this integral. So we just plug this in here, everything else here stays the same. Let's check it. Here, everything stays the same. We have the basis functions of the infinite square well potential. Then here we have a, the constant, which we found here, x, a minus x. X, a minus x, dx. So this integral is coming directly from equation 240. Now, I'm not going to take a look at this. Simplify, boom, 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 move things around, boom, and you get this number. Again, or actually you don't get this number because it depends on n. You get 0 if n is even, and you get this thing here if n is odd. Okay. Now, we just plug this into the original equation, and you see how n is even gives you 0? That means we only take the n equals odd terms, 1, 3, 5, and so on. And we keep everything the same sign, this stuff here, the normalization constants, e to the whatever, and this thing over here. So this looks a bit crazy. Maybe it's better to do it on paper and kind of see what's going on. Alright guys, actually I'm not going to do this problem today, maybe in another video. The video is already getting so long. So that was the section of the book which was the infinite square well. Thank you guys for watching. I hope you found something useful in this video, and I will see you guys in the next video, which is section 2.3, the harmonic oscillator. Peace.